Hello everyone, I hope you all are doing well, and tonight I'm going to be kinda taking you guys through my mouse. My mouse is being problematic. Of course it's dead. Okay, cool, so I got my mouse working. So, hi, mouse, please, cooperate. I beg of you. Okay, it doesn't want to cooperate. Okay, cheers. Let me just very carefully move my mic over here, that way I can get to the trackpad. Okay, so, anyways, tonight I will be going through my study routine for my chemistry course. And what we're doing right now for my general chemistry 2 is just close out of all the other tabs, is going over properties of solutions, like vapor, ignore that, it's embarrassing, like vapor pressure and molarity, very basic things like that. And eventually we're going to get into thermodynamics, like the very basics. And yeah, that's pretty much it. So I'm just going to get on my Canvas page to the textbook, which is Gilbert's 3rd edition, Chemistry in Atoms-Based Perspective. And while that's loading, I'm going to get out my notes. I have all my stuff for this semester in a lovely dossier. That way it's all organized. I'm not allowed. Sorry. That way it's all organized. And yeah, it's not like big and bulky, like carrying around like a giant notebook. Plus, the ones I had, the notebooks I had, kind of fell apart after a while. So they end up just being like sleeve binders, in essence. So I'm gonna be making this into kind of a Cornell notes template. If I have space, I don't want to make a loud noise. Oh, cool, my mouse is charged. It might have been also loud. Okay, so here, come on. I swear, this mouse. You were connected like 3 seconds ago, come on. So now it's connected. And I'm going to be... I wish I had enough space to be able to... Oh wait, I have an idea. I have a Lenovo, so I could just do this. Wow, guys, it bends. Ignore the serious damage on the front left here. That's nothing, you know, that's just the flesh wound, you know, it'll heal right up. Thank you. Cool. So, now that I have space, I'm gonna move my mic over here. I'm gonna move my paper over here. So, hold on. Just adjust it so that you guys can see what I'm doing. And here's the paper over here. You probably won't be able to see what I'm doing, but that's okay. Yeah. Okay, so now you should be able to see what I'm doing. And let me get a pen. You might hear some people in the background being loud. You might hear some people in the background being loud. And that's because I'm in a study room that I reserved, like, for the university. But, it's still kind of loud. So I'm writing with this lovely fountain pen here. Come on, okay. As you can see from the lovely nib, it is indeed a fountain pen. And I kind of like. So is, like, I'm also taking an education course, and I kind of knew this before, but, beforehand, before taking that course, but, basically, different activities, learn different, like, things with a different, like, level of profundity, and things like, for instance, what the Cornell Notes does is, for the summary, that allows you to achieve what an education is called, analysis, like, is classified under, like, the Bloom's taxonomy is what it's called, as analysis. And I'm going to navigate over to vapor pressures. That's what I really need to study, since I don't really understand it. Like, not the math and stuff behind it. Oh my god, I wish. I really wish I could petition McGraw-Hill, or whoever it is who makes this ebook company, to add a dark mode, because now I kind of have to zoom in, which with the screen folded out like this, because like my touch screen got messed up, so I have to zoom in a lot in order for it to be visible for me from a distance, and probably so that you could read it off the screen too. So 11.3 vapor pressure. Ask yourself what happens if you leave a glass of water on a kitchen counter for several days. If the glass is left undisturbed, the water level drops as the water slowly evaporates. At the particle level, some of the molecules of H2O on the surface escape from the liquid and enter the air above it. They can escape because the water molecules at the surface of the liquid have a distribution of kinetic energies, as we saw with the gas phase molecules in chapter 9. I'm not going to go through that because I don't really want to. And some of them have sufficient energy to overcome the intermolecular forces holding them on the water. Basically this. Yeah. Wow, that's really zoomed in. If an identical glass of water is left covered on the same counter, water molecules will evaporate at the same rate, but they're confined to the space above the water and below the cover. Basically what it's getting to, I don't want to read all this, I'm not only am I lazy, but I also need to like study this myself. But what it's getting to is that eventually the amount of water vapor in the air in the covered cup will, like, the pressure that it exerts on the pressure that the liquid and the pressure that the gas, I might not be getting this right, which is why I need to study this, is equal. Yeah, I think that's what it's saying. The rates of evaporation and condensation are the same as molecules on the surface. Yeah, pretty much. Yeah, okay, cool, that makes sense, yeah. It's kind of like what I'm saying. Water vapor in the spot, water in the cover glass, pressure. Yeah, so when the amount of gaseous atoms of, it could be water, it could be any like liquid or gas in a space is equal to the amount of atoms of gas, then that's basically the vapor pressure. The pressure that the gas exerts upon the liquid is the vapor pressure. A liquid is said to be volatile when enough of its molecules vaporize to produce significant vapor pressure. I think it's talking about statistically significant, so over 5%, depending on the p-value. And I could probably make a whole other video discussing statistics, except I don't really understand statistics that well enough. I got a B in Intro to Scientific Data Analysis, so I don't really know statistics that well. I know enough to write some more code. Anyways, maybe this is why I need to study this. I need to read it more in detail. Maybe not. This kind of makes sense to me. So essentially, like, I'm just gonna be skipping ahead to what I need to study. I'm basically just like, kind of like the Feynman technique in a way. Oh my god, that's a pretty good idea. I could just make ASMR content. It's literally just me studying. That way I could like learn how to explain things in simple terms. Wow, that's crazy. Okay, anyways, you guys are using this to fall asleep anyway, so I don't think you actually need to like know this stuff. So, the Clausius Clapeyron equation. I can never say that and I can never spell it. That's why I can never Google answers to like any of this, because I would just misspell it. But that Clausius Clapeyron whatever. So the vapor pressure of a volatile liquid increases with increasing temperature. Which, if you look at a phase diagram, I can't pull it up because I can't type because I folded it on my computer because I'm dumb. But basically, the vapor pressure of a volatile liquid increases with increasing temperature, and this figure 11.7, somewhere down there, shows the increase is not linear. However, if we graph the natural logarithm of the vapor pressure versus 1 over T, where T is the absolute temperature, meaning in Kelvin, we do get a straight line. The slope of this line depends on the enthalpy of vaporization for the liquid. So this is the Clausius Clapeyron equation. I think I'm pronouncing it right. If I don't pronounce it right, I honestly don't care at this point. Where R is universal gas constant, 8.34 joules per mole per Kelvin, and C is a constant that depends on the identity of the liquid. I've also heard C, like, in regards to this equation, not just like in calculus, because this is a calculus thing, I think. But C, I think, is like a y-intercept too. But that makes sense because it's a, yeah. We could use equation of more theory for the pressures of two temperatures. So this. Sorry, I had to yawn. So yeah. And this is what I really struggled with because I was working on like the assigned homework for this, and like that was actually painful. Like I could not do it for the life of me. I will admit I am trying to get ahead of where the rest of the class is, just because I kind of like to have a bit of cushion. That way, if I take longer to understand something, I don't have to be like trying to understand the concept while trying to stay caught up with the class, you know. So I try to work ahead, just so that I could have some wiggle room as far as like getting a more profound understanding, you know. So this is the Clausius Clapeyron equation. We use it to calculate the vapor pressure of a liquid at any temperature if we know its normal boiling point and enthalpy. This delta H for triangle H is enthalpy. So this is the plot of the natural log of the vapor pressure as a function of 1 over the absolute temperature, and this is basically showing why the Clausius Clapeyron, I'm just going to call it the CC equation, why the CC equation is so useful, because chemists like things to be linear. They don't like exponentials, because exponentials are really hard to find like a definite value for. Yeah. So let's go through a sample exercise. I kind of need to do that anyway, so I might as well do it on camera. The compound with the common name isooctane, its official name is 2,2,4-trimethylpentane, as the structure shown in figure 11.9. It defines the 100 value on the octane rating scale used to grade gasoline. Its normal boiling point is 99 degrees Celsius, and its enthalpy of vaporization is 35.2 kilojoules per mole. What is the vapor pressure of isooctane at 25 degrees Celsius indoor? This is actually was so bad. Not even funny. That's why I'm like a pre-med now. Because people have told me, dude, you should be a doctor with that freaking handwriting. And I've now started to agree with them. Shit, that was loud. Hopefully the AAMC agrees with them. So, my chemistry courses have used the COAST method, which stands for collect. So, like, look at a problem, see what it gives you, see what you kind of have and don't have, organize, which is basically planning how to go about solving a problem. Analyze, which is analyze is where you kind of plan out solving the problem, plan out what steps to take, plan out things like whether or not your signs will cancel, things like that. For instance, it's talking about temperatures on the Kelvin scale and conversions and things like that. Solving is actually doing the problem, and the T is for think, but it's really think about it. Well, that's what it is on the textbook. But I was taught that it was just think, which is just make sure think, is your answer reasonable? Does it make sense? So let's go through the GHOST framework for this problem. We are given the normal boiling point and enthalpy of vaporization of isooctane. We are asked to calculate its vapor pressure at 25 degrees Celsius. The Clapeyron CC equation relates the vapor pressure values of the liquid at two temperatures to its enthalpy of vaporization value. To use the CC equation, we must express temperatures on the Kelvin scale and convert delta H to joules per mole. To be compatible with the units on our joules per mole per Kelvin, or times Kelvin, vapor pressure decreases sharply as temperatures decrease below the normal boiling point of the liquid, so the vapor pressure of isooctane at 25 degrees Celsius should only be a fraction of the ambient atmospheric pressure, 260 torr. And that kind of goes into the thinking part, determining if your answer is right, and if it's not right, where you went wrong. So the heat of vaporization in joules per mole is 352 kilojoules per mole times 1,000 joules. Yeah. That's the thing about heat of vaporization and about the gas constant. They both have to be in joules per mole. They can't be in kilojoules per mole. And, for the gas constant, they have to be in kilojoules per mole. So, this is what they did. I really don't want to work it out by hand because the CC equation scares me, and I always end up messing up somehow. And in hindsight, I think that might have something to do with, maybe me using the wrong units or something like that. Is my face in the frame? I think my face was in the frame. I think my face was in the frame. Slightly. Might have been. I don't know. Doesn't matter. I'm just gonna move my phone over a bit. But, being an education minor, and considering that, I'm gonna start, fuck, that was loud. Okay, I need to edit that out. Let me just take a count of it. Okay, that was out. Just a little bit of note taking there. I think that was because I breathed. That really sounds weird, but I'm not a linguist. I'm also not one of those pretentious people because I'm a programmer. Fuck, that was about to. Okay, so basically, I breathed into the microphone with my nose, and it was pretty loud. So I'm gonna edit that out. Anyways, so this is what they did here. they plugged in a 760 Tor to the initial. Oh, that's what I was doing wrong. I always put in 760 Tor as the final. Oh my god, I'm dumb. Anyways, so, and they're plugging in this, which they called into joules per mole. They're plugging that in there, and then they're dividing it by the R, which is always 8.04. That messed me up too. And they're plugging in. Where did Bro get that from? Because, hold on, let me see the parameters here. Yeah, okay. Okay, oh, okay. So, D1, and their second temperature was 25 degrees Celsius, so they added that to the Kelvin. But where'd they get 372 from? Oh yeah, because oh my gosh, that's what I was doing wrong too. They added the boiling point. Okay, cool, I think I know where I went wrong now. Yeah, I was doing some homework a little before making this video, and I was really like considering whether or not I even wanted to make this video, just because I really wanted to get that homework done, and I was really struggling on it. And so I was really like plugging in random numbers and like putting in the most random stuff on Desmos I could possibly think of. But now that I actually made the video, and I'm making the video, and now that I am actually doing, like, going through the book with full detail, like, not even for studying, well, kind of for studying, but mainly for the ASMR, I actually received, like, a bit of benefit from it. That's pretty cool. Okay. Fuck, I breathed on the mic again. Grab me. Cool. I'm gonna edit that out too. Just adjust the mic a little bit here. Oh my god. So, I will think about it when I actually do a problem, but I don't want to read that because I'm lazy. I guess we do the concept test. Diesel fuel is made of hydrocarbons with an average of 13 carbon atoms per molecule, and gasoline is made of hydrocarbons with an average of 7 carbon atoms per molecule. Which fuel has the highest vapor pressure and temperature? Okay. So, I guess I could kind of do this and explain some of the chemistry behind it. So, because these are both made out of hydrocarbons, there's no capacity for hydrogen bonding. Hydrogen bonding is like what happens when water sticks to itself, like other water molecules stick to other water molecules, and like it's why, if you've ever seen like a glass, that's why there's a curvature on it. Or like if you look at like, let's say, what's a good example? Like a graduated cylinder, or like a thinner glass thing, maybe not a glass, but like maybe the neck of a bottle or something like that. The water adheres to the silica in the glass, and it hydrogen bonds, so it's not a real bond, it's just an attraction. Well, because these are hydrocarbons, we don't have to worry about that. I don't want to get into it. I probably could, but I don't want to. This video is long enough. So, this is 13 carbon atoms. This is 7 carbon atoms. They're both an odd number of carbons, so they're asymmetrical. Or maybe they are symmetrical, actually, never mind. But, typically, the heavier atoms, they have a greater potential, or they have a greater, like, momentum, like inertia. I'm kind of thinking physics here. This is like what I'm thinking. This is how I would logically move through this. So because gasoline is lighter, I would say that gasoline has a higher vapor pressure. Plus, like at gas stations, you typically smell gas, not diesel, because gas is volatile, diesel is also volatile, but I think it's just less so. Could be that, or could be the limitations of human scent. So, let's see if my logic is correct. About, yes, probably not for the same reasons, but yeah, that's basically it. Anyways, I have breathed into the mic enough and struggled with my mouse, and basically use this channel for my own academic gain. So I hope you all enjoyed. I hope this was relaxing. And if you happen to scroll down to the comment section, let me know what type of content I should make, like in the future. Like if I should continue doing this like studying kind of thing, or if I should read more, or if I should like maybe do. I can't really do roleplays right now since I'm in college. I don't have time or money to spend on props or anything. But let me know what I should do, and I hope you all have, like, I guess, a great rest of your nights. Even though if you're watching this, you're probably gonna sleep, but whatever.